Hello everyone, welcome to Basic Electronics Tutorials. In this video, I am going to discuss on Bipolar Junction Transistor, in short a BJT. Let us start this discussion by asking ourselves first the basic question, what is a Bipolar Junction Transistor? A BJT is a simple semiconductor device that can be used for either amplifying electrical signals or for switching electrical power. Please note, it is mainly used as an amplifier or as a switch. So the next important question is, how is it constructed? A BJT can be said as an extension of a PN junction diode and is constructed by adding either a N-type or P-type semiconductor region to a PN junction diode. Please note, I have discussed PN junction diode and its working principle in one of my previous videos. That video will be a prerequisite for this, so I would highly recommend you to watch that video first. You can watch it by clicking on the link shown in the top right corner right now, or I'll leave the link of the same in the video description below. Coming back to the topic of this discussion, we learned that a BJT is simply an extension of a PN junction diode and is constructed by adding either a N-type or P-type semiconductor region to a PN junction diode. Let us look at how this is done. Figure 1 here indicates a BJT construction. Let us start by considering a simple PN junction diode, which is this part of the device. As I said, if an N-type semiconductor region is added to a PN junction diode, then we get an NPN transistor as what is shown here. In a very similar fashion, if I consider the PN junction diode in this part of the figure, by adding a P-type semiconductor region to a PN junction diode, we get the PNP transistor. So, we understand that adding an N-type semiconductor region creates an NPN transistor and adding a P-type semiconductor region creates a PNP transistor. To give you more idea about how this device looks like in electrical terms, I have shown these two diagrams. Let us consider the NPN transistor first. If you look at the NPN transistor, you can see that the first two semiconductor layers, which is let us say 1 and 2, form a diode which is shown here. N-type will be this one, P-type will be this one. By adding another N region as what is shown here to a PN junction diode, we will create one more diode which is formed by the next two semiconductor regions. That is shown here. So, we have NP and then we have a PN. So, therefore, this forms NPN. The same principle can be extended for the PNP transistor as well. If I take this as 1, this as 2 and this as 3, the regions 1 and 2 form this diode, and adding the third region which is the P region as shown here, we will obtain another diode which is shown here. So, this is PN because this is positive, this is negative, and this is negative and this is positive, therefore, it is NP. So, this will create a PNP transistor. The device so constructed will exhibit two junctions. The first one is across the first two semiconductor regions and the second one is across the second two semiconductor regions. We can call them as junctions J1 and J2 respectively. It is because of the presence of these junctions that this device is called as a junction transistor. So, why do we call it as bipolar then? It is called as a bipolar device because during the process of turning on as well as turning off of the device, the process involves both positive and negative charge carriers. This is the reason why we call it as bipolar junction transistor. Please note, it is called as bipolar because it uses both positive and negative charge carriers for turning on and turning off, and then it exhibits two junctions in its structure and hence the name bipolar junction transistor. Also, you must note that each semiconductor region in a BJT has a terminal attached to it. So, this is one terminal, this is second terminal, this is third terminal. So it is a 3-terminal device. The symbolic representation of the BJT is as shown in figure 2 here. The first diagram here is for the NPN transistor and the second diagram is for PNP transistor. We differentiate the two symbolic representations by looking at the arrow as what is shown here. For an NPN transistor, the arrow is pointing out of the device, and for a PNP transistor, the arrow is pointing towards the device. Let us now understand how and why this arrow specification is used for NPN and PNP. For that, we will be once again using the figure 1 here. Let me first consider a simple PN junction diode as what can be seen drawing on the bottom of the page. For this particular representation, the left terminal is the anode and the right terminal is the cathode. The diode is a unidirectional current carrying capability device. So, the current direction through this device is always from anode to cathode. So, this is, let us say, ID. So, now let us apply this principle to the NPN transistor shown here. Let me now talk about the diode D1, which is to the left of the NPN transistor. I will call the other one as D2. Since the diode current can only flow from anode to cathode, for this NPN device, the current direction for diode D1 is like this. Coming to the PNP device, once again coming for the diode D1 here, the current direction is always from anode to cathode, so it is reverse to that of the NPN. So, if you come back to the NPN transistor, you understand that the diode D1 current direction is flowing out of the device, whereas that for PNP, the diode current direction is towards the device. This current direction is represented in the symbolic representation here. So, for NPN, the arrow should point outwards, and for PNP, the arrow should point inwards. This is how you can remember the NPN and PNP symbolic representations. Let us now talk about forward or reverse biasing this device. Please note, even though it is a simple extension of a diode, the doping concentration of the regions of the BJT are not all same. The three regions, which are NPN or PNP, have different doping concentrations. The highest doped semiconductor region in a BJT is called emitter. The medium doped region is called as the collector, and the least doped semiconductor region is called as the base. So, we understand that each of the region has different doping concentration, and based upon the doping concentration, we have named those regions as emitter, collector and base. Emitter has the highest doping concentration, then comes the collector, and lastly we have the base. The next important thing to discuss is about the area coverage. If you look at the way in which I have written the diagram here, you will note that the leftmost N-type semiconductor region in the NPN transistor has medium area coverage. The rightmost N-type semiconductor region has largest area coverage, and the middle P region has the smallest area coverage. So, which one among them are emitter, collector and base? The highest coverage area region is called as the collector. The medium area coverage region is called as the emitter, and the lowest area coverage region is called as the base. This is the reason why the terminals of each of the semiconductor region are denoted with the first letter of the corresponding names. E here stands for emitter, B stands for base and C stands for collector. So, whenever you want to draw a BJT, you first write a box and then divide the area coverage. The middle region always must be the smallest region, and this region is called as the base. The largest area coverage is always for the collector, and the remaining one is the emitter. This is how you can draw a BJT. Please note, you have to show terminals as well. This particular way of drawing the diagram is applicable for both PNP as well as NPN transistors. Continuing our discussion on biasing the transistor, let us now talk about the two junctions. We already have discussed that by adding another semiconductor region to a PN junction diode creates a BJT. Because of this way of construction, we get two junctions in the structure of a BJT. Let us call them as junction J1 and J2. Temporarily, we will call them like that. Now, we have to understand where these junctions are placed. It is very clear here. The junction that is formed between emitter, which is this semiconductor region, and base, which is the middle semiconductor region, this is called as base to emitter junction. In a very similar fashion, the junction that is formed between the collector and the base is called as collector to base junction. It must be noted, these two junctions play a very vital role in the operation of the BJT. Particularly, based upon the way in which these two junctions are biased, a BJT can be operated in three regions. Let us now talk about that. Let us consider the table that is shown here. As I said, there are two junctions, base to emitter junction, which is shown in the leftmost column. Then we have the collector to base junction, which is shown in the left second column. The third column here indicates the region of operation, and the last column, which is the rightmost column, indicates the application for which that particular configurations are used. Let us consider this particular row. When both the base to emitter junction and collector to base junctions are reverse biased, then the BJT operates in cutoff region, and during this region the BJT is said to be in the off state. So, the applications for this are not much. That is why I have mentioned it as nil. Moving on to the next one, if the base to emitter junction is forward biased and the collector to base junction is reverse biased, then we get active region of operation, and this has a very significant application where the BJT is used as an amplifier. Lastly, when both the base to emitter junction as well as the collector to base junction are forward biased, the region of operation is called as saturation region, and in this region a BJT can be used as a switch. If you look at the application column here, you would understand when I was answering the question for what is a BJT, I said it is a simple semiconductor device used either to amplify electrical signals or switch electrical power. So, you will note here from the last column that they are the major applications of a BJT. So, we can now conclude that if we desire to operate the BJT as an amplifier, then it must be operated in the active region, and if you want to operate the BJT in the active region, then the base to emitter junction should be forward biased and the collector to base junction should be reverse biased. In a very similar fashion, if you want to use the BJT as a switch, then it should be operated in the saturation region, and if you want to operate the BJT in the saturation region, then both the base to emitter junction as well as the collector to base junction must be forward biased. Right, now we have understood that there are two junctions. We have to bias the junctions in a certain fashion to operate the device either as an amplifier or as a switch. So, the obvious question that arises now is how to bias these two junctions. We say that to use the BJT either as a switch or as an amplifier, we need to bias the junctions in a certain fashion, and biasing them requires applying voltages to the terminals. We have previously learned that a BJT has three terminals, and therefore we would require at least two voltage sources to bias it. So, you may now ask the question, how to provide two voltage sources to three terminals? This is done by keeping one of the terminal as a common terminal and applying voltages to the other two terminals to bias the BJT. Now, since there are three terminals, we will now have three options for biasing a BJT. These techniques are also called as configuration techniques. We call them as BJT configuration techniques. If I consider the base terminal as the common terminal and apply voltages to the other two terminals, that is emitter and collector, then the resulting configuration is called common base configuration, because the base is considered as common terminal. In a very similar fashion, if I take the emitter terminal as common and I apply voltage to the other two terminals, which are base and collector, the resulting configuration is called as common emitter configuration. And lastly, if the collector terminal is considered constant and voltages are applied to the other two terminals, which are emitter and base, the resulting configuration is called a common collector configuration. It should be noted that the behavior of the device under these three configurations is completely different. In fact, the three configurations shown here have completely different characteristics, and I'll discuss each one of them in complete detail in the next videos. Let us now very briefly discuss the three configuration techniques for a BJT. I'm going to start the discussion with the common base configuration first. To explain the configuration, I have shown the source voltage connections to the three terminals of the BJT for both NPN as well as PNP. You must note the only difference between NPN and PNP when it is connected to voltage sources is simply the polarity difference. That is, all the positive voltages in the NPN transistor will become negative voltages in the PNP, and all the negative voltages in the NPN transistor will become positive voltages. The same applies for the currents as well. A positive current in NPN becomes negative current in PNP, and a negative current in NPN becomes a positive current in PNP. So, if you remember the voltages and currents for one transistor, you can simply reverse the same and write the circuit for the other transistor. For this particular video, let me consider the NPN transistor for the explanation. As I previously said, it is all about forward biasing or reverse biasing the junctions. Let me mark the junctions very quickly here. The junction that is formed between the base and emitter is called as the base to emitter junction. So, let me call it as JBE. It is base to emitter junction. And the junction that is formed between collector to base is called as collector to base junction, or simply JCB. Now, as I said, if both of the junctions are reverse biased, the device operates in the cutoff region, and when I say cutoff region, it simply means it is off. There is no application of that. Let us now talk about the active region. In the active region, you must note the base to emitter junction should be forward biased and the collector to base junction should be reverse biased. So, now we have to provide voltage sources across the terminals in such a fashion that the base to emitter junction is forward biased and the collector to base junction is reverse biased. Once again, you must recall the way in which a diode is forward or reverse biased. If I consider a simple PN junction diode, if I connect a positive terminal of the supply to the P semiconductor region and the negative terminal of the supply to the N semiconductor region, it will forward bias. If I reverse the voltages across the supply, then the diode becomes reverse bias. So, now we can treat these two junctions as if they are simple diodes. So, let me first concentrate on the junction between base and emitter region. As I said, for the active region of operation, the base to emitter junction should be forward biased. To forward bias a PN junction diode, the positive voltage should be connected to the P type of the semiconductor, negative voltage should be connected to the N type of semiconductor. Because of this, as you can see the voltage across the emitter here, the positive terminal of the supply is connected to the P semiconductor region and the negative is connected to the N semiconductor region. This type of voltage application will forward bias the base to emitter junction. Let us now talk about the other junction, which is between the collector and base. Since I want to operate the BJT in the active region, the collector to base junction should be now reverse biased. If you look at the right two semiconductor regions, we have P and N. If I want to reverse bias, what should I do? I should connect the positive terminal of the supply to the N semiconductor region and negative terminal of the supply to the P type semiconductor region. That is exactly what is done here. So, N type semiconductor has a positive terminal attached to it and P type semiconductor has negative terminal attached to it. Please note the polarities are shown wrongly here. This is positive, this is negative. So now we have forward biased the base to emitter junction and reverse biased the collector to base junction. This will make the transistor to operate in the active region. By using a very similar approximation, if you want to operate the transistor, let us say in saturation, you have to provide appropriate voltage to forward bias the collector to base junction. If you look at the PNP transistors shown to the right, you can understand the voltages are completely different. Look at the voltages here and here, they are opposite to each other. And also look at the way in which the current directions are flowing. For the NPN, the emitter current flows out of the device. For a PNP, it flows towards the device. The diagrams that are shown below here as well as here use the symbolic representations for the NPN and PNP transistors for the same configurations what we just discussed. Let us now move on to the common emitter configuration. Please note this is one of the most commonly used configuration. What is common emitter configuration? It is a configuration in which the emitter terminal is taken as a common terminal and voltages are applied across the other two terminals. So you can see the emitter terminal here is common to both the base as well as collector terminal. And let us say now I want to operate the transistor as previously in the active region. So for active region of operation, the junction between base to emitter should be forward biased and the junction between collector to base should be reverse biased. Let us now talk about the base and emitter junction first. Since this has to be forward biased, I will provide a positive voltage to the base terminal and a negative voltage to the emitter terminal. This will forward bias the base to emitter junction. Now coming to the collector to base junction, I have to now reverse bias it. But the problem is the voltage is connected across collector and emitter, not across collector and base. So how to understand this? For that you have to understand the potential difference across the terminals. If you look at the base terminal shown here, what is the potential? It is positive. In a similar fashion, if you look at the collector terminal here, the potential is also positive because it is connected to the positive terminal of the supply. Please make this correction. Generally, the values of voltages that are supplied here, they are not the same. Commonly, the value of VCC is high as compared to that of the VBB. This value of voltage will directly reflect on the corresponding terminals. So we can say that the collector is at a high potential and the base is at a low potential. So where is the collector connected to? The N-type semiconductor region. Where is the base connected to? The P-type semiconductor region. And if you look at the potential, the N semiconductor region is at high potential and P semiconductor region is at low potential. Therefore, you have to now understand that the potential across the collector to base junction is negative, because of which it will get reverse biased. This is how you are going to operate the common emitter configuration circuit in the active region of operation. If I simply reverse all the voltages and currents, I can apply the same principle for the PNP transistor. Once again, down here I have shown the original circuit diagrams which uses the symbolic representations of the BJT. There is a small correction required in the polarity of VCC for NPN transistor. This is negative, this is positive. Lastly, let us now discuss the common collector configuration. What is this configuration? It is a configuration in which the collector terminal is taken as common. Look at this. And voltages are applied across the other two terminals which are base and emitter. Once again, I will illustrate the operation for active region of operation. For the active region of operation, the junction between base and emitter, this should be forward biased, and the junction between collector to base, this should be reverse biased. Right? So since there is no voltage connection between base to emitter, let me come back to that a little later. Look at this, there is a voltage supply connected between collector and emitter terminals which is VEE. Since I want the collector to base junction to be reverse biased, I'll apply a positive voltage to the collector terminal, and alternatingly I have to apply a negative voltage to the emitter, because that is what is the connection. In a very similar fashion, if I come to the base to emitter junction, since I want this to be forward bias, I will apply a positive voltage to the base terminal, as what can be seen here. Now, the problem is there is no connection between collector and emitter internally. It has to go through the base only. Therefore, I have to now analyze the potential differences across the three junctions in order to understand whether the junctions have forward biased or not. If you look at VBB here, the positive terminal of VBB is connected to the base terminal, and coming to VEE here, the negative terminal of VEE is connected to the emitter. If you now analyze the potential difference across base to emitter, you will note that base is at positive potential and emitter is at negative potential. Because of this, the base to emitter junction will be forward biased. Coming to the collector to base junction, note that the positive terminal of VEE is connected to the collector terminal. So, the collector now is at positive potential, and the base terminal, as we previously discussed, is also at a positive potential. So, we have to now analyze the potential difference. As previously said, the value of the voltage applied across the collector is always high. So, the collector is actually at a high potential, and the value of voltage across the base is always low. Therefore, the base is now at low potential. Look at this, collector is at high potential, base at low potential. This means that the potential difference across the N and P region, which form the collector to base junction, is in fact negative. This will cause the collector to base junction to reverse bias. Once again, by reversing all the voltages and currents, the same explanation can be fit for the PNP transistor as well. Down here, I have shown the circuit diagrams using the original symbolic representations for NPN and PNP transistors. Let us now talk about the currents in a BJT. Since there are three semiconductor regions, BJT exhibits three types of currents based upon the region of current origination. The current that is originated from the base region is called as the base current. The current that is originated from the emitter region is called as the emitter current, and the current that is originated from the collector is called as collector current. Let us now consider the basic structure of a BJT as what is shown in the bottom of the page here. We know that the emitter has the highest doping concentration, collector has medium doping concentration, and base has the lowest doping concentration. By the principle of transfer of energy, when the BJT is forward biased either in active or even in saturation region, the charge carriers from the emitter region move towards the less doped base region. This is the flow of charge carriers from the emitter. Some of these charge carriers that were originated at the emitter now recombine with the opposite type charge carriers in the base region, and the remaining charge carriers along with the charge carriers of the base region will then move towards the collector. Please note the arrows what I have shown here indicate the direction of the charge flow. We know that the flow of current is opposite to the flow of charge carriers, and the current direction is therefore from the collector towards the emitter. This is a very important point to note. So, if I write an equation for the charge carriers stored in each region, I can say charge carriers stored in the collector is simply the sum of charge carriers from the base region plus the charge carriers from the emitter region. On the other hand, if I write an equation for the current, then it is actually the sum of base current plus the collector current, which forms the emitter current. This is a very important equation in BJT. Right, let us now summarize our discussion on BJT. We learned that it is a three-terminal device, and the three terminals are emitter, base and collector. A BJT is constructed by adding either a N-type or P-type semiconductor region to a PN junction diode. Therefore, two junctions will be created within the device structure. So, we can call it as a three-terminal two-junctional device. Based upon what type of semiconductor material is added to the PN junction diode, we can have two types of BJT. The first one is the NPN, the second one is the PNP. Since it is the input current that controls the turn on and turn off of the device, you must note it is called a current controlled device. Also, the forward biasing or reverse biasing of the device uses both positive as well as negative type of charge carriers. We call it as a bipolar device. However, you must note it conducts current only in one direction and therefore it is a unidirectional device. Coming to the important applications, if you want the BJT to operate as an amplifier, then you must operate it under the active region where the junction between base to emitter is forward biased and the junction between collector to base is reverse biased. On the other hand, if I want to use the BJT as a switch, then it must be operated in the saturation region where both the base to emitter junction and the collector to base junction must be forward biased. Lastly, since it has three terminals, there are three possible ways in which you can connect the BJT to the power supply and we call them as configurations. The three configurations are common base, common emitter and common collector. In my next videos, I will be considering each one of these configurations in complete detail and there we will also discuss about the characteristics of the device in each configuration setting. So stay tuned. Well, with that we have come to the end of this video. In my next video, I will be discussing on the common base configuration of a BJT and its characteristics. If you found this video to be informative, kindly like and share this video and subscribe to my channel for more tutorials on basic electronics. Thank you for watching. Have a good day.